everyone, I'm Maheep Singh, and this is my third presentation for the GSOC 2025 3 requirements, Task 3. And the topic of this presentation is the basics of shader for flutter animations and gradients. For this presentation, I'll be going through some slides along with a few demo to help you understand how we can write shaders. And in the end, I'll show you how we can integrate shaders into a flutter application. So before we move on how to write shaders, first we need to understand what a shader really is. So you can think of shaders as a set of instructions which are executed all at once parallelly. And these instructions tell each and every pixel on the screen how to behave. So according to the position of the pixel on the screen, it tells the pixel what color it needs to take. Now what makes these shaders fast? For that, we need to understand the difference between a CPU and a GPU. Now you can imagine a CPU as a set of, think of them as 4 to 8 big pipes, and every task can be thought of as a box which has to pass through these pipes. Now some tasks are bigger, and hence they are bigger boxes which require more processing power, or think of it as more time to pass through the pipe. And now each of these tasks has to move through these pipes one by one, and one pipe can only have one box moving through it at once. Each of these pipes is known as a thread. Now imagine that you have to render a screen for say a video game, and now every pixel on the screen needs to be computed. So assuming your game needs to run on a 1920 x 1080p screen, a modern 1080p display, that is roughly 1 million tasks to be computed by a CPU every 1/60th of a second for a 60 fps frame rate. Now, even though uh, doing the calculation for each pixel is relatively a small task, a CPU cannot handle this magnitude of calculations all by itself in a single second. Now, what is the solution to this? The solution to this is parallel processing. So, as you can see in the pictures, you can imagine the GPU as a set of uh, a lot of small and less powerful pipes as compared to a few set of large pipes, which is a CPU. So in GPUs, instead of a couple powerful or big microprocessors, we have lots of these pipes which run in parallel at the same time. And each pipe only has to handle a small fraction of the total number of calculations, which is a lot more feasible as compared to having just a few big pipes process a million of these calculations every second. Now, shaders give instruction to these pipes or the GPU on how to calculate each pixel individually at the same time, and this is what makes these shaders fast. Now, one important thing that you need to keep in mind while writing of shaders and thinking of shaders is that these pipes, they do not have access to what another pipe has calculated. So each pipe receives the same set of inputs and must calculate its output individually. That is to say that in GPU, the threads do not have access to what the other thread is processing. So no thread-to-thread communication is taking place. The threads are totally memoryless, so they also do not know what they last rendered. So when we are writing shaders for Flutter, we will be writing them in a a Flutter supported shader language known as DLSL or OpenGL shading language. Now, before we move on to writing our first shader, I'll tell you what the difference between fragment and vertex shaders is. Flutter only supports fragment shaders, and what vertex shaders are is that they process each vertex of a 3D object, while fragment shaders process each fragment, which is usually a pixel, based on its say position or time since the shader has started rendering to determine the color of the pixel. Throughout this presentation, we'll be focusing on fragment shaders only because they are the only ones that are currently supported by Flutter. Right, so we first need to understand uniforms. Now, because of the architecture of threads in the GPU, the input that we receive from CPU for each thread is equal and is also it is read only. So for each thread, it will be getting the same data, and this data is known as uniform because it is uniform for all the threads of the GPU. So as you can see in the code snippet shown here, we have hash ifdef gl underscore es precision medium float endif, and then we have three uniforms defined here: the resolution, the mouse, and time. The resolution tells you the canvas size, that is the width and the height of the screen. The mouse will tell you where your pointer is placed in terms of pixels of the screen, and the time is basically the amount of time that has passed since the shader loaded. And now what about this code on the top? If def gl underscore es precision medium float. It basically first checks if gles is defined, and if it is, it sets the variable or level of precision for any floating point variable to medium here. And the lower the precision, the faster your shader will load, but also the worse the quality of the shader will be. And in shaders, we utilize float. Throughout shaders, all you will mostly be using is from 0 to 1. So the accuracy of the shader to the amount till the float is defined becomes vitally important for how accurate and how high quality your shader is. And that is being defined here at the top. Uh, right. Also, what you need to keep in mind is for shaders, as I said before, floats are extremely important. If you just write 1 or 0, even they might sometimes not work. So you need to write even 1 and 0 as 1 point and 0 point. So you need to utilize float throughout. Now, before we move on to GL coordinates and GL color, basically all you really need to understand here is the default output for any shader is for any fragment shader will be GL frag color. I'll show you your before we really get into frag coordinates and frag color. I'll show you your first shader, which is going to be our equivalent of hello world, but in shader language. And this is the equivalent of hello world in shader language. Uh, I'll comment out the complicated part and show you the simplest shader that you can write. All it does is it takes the output and sets it to a constant vector of 1.0, 0.5, 1.0, and 1.0, which essentially represents this color. Now, what are these four numbers you see here? It represents the R, G, B, and the opacity value of the color that you see here. Now, I have already introduced you to uniforms, so I'll give you a short demo on how uniforms work. I'll comment out this hello world code, and I'll put in this color, this code. Now, as you can see, as I move my mouse along the canvas, the color of the shader changes. Now, what is happening here? First, we get the resolution, and we from the resolution we get the first two, or the x and y coordinates of the resolution. So that will give you your width and your height, the x and y, and then we get the mouse position and also get the xy for it, and then we normalize this position. What I mean by normalizing is suppose we have 1024 pixels and your mouse is in the center, so 512 pixels, so you divide 512 by 1024 and you get 0.5. As I already told you, all of the operations in vector is handled in floats, so you need to normalize everything. And then what we do is we set color to a vector of pause. Now what does this do? This syntax is basically the same as writing this. Uh, sorry. So what does this do is, since pause is already a vector of 2, which is essentially an array having two elements in it, it sets the color array to the pause array and sets the frag color. Here what it is doing is it will take the first two elements of color, or the two elements of color essentially as its first two elements, and 1.0 and 1.0 will be the other two values, which represents the blue value and the alpha value here. And RG will be set by the position of our mouse coordinates. So that was me explaining your first shader ever, or the equivalent of hello world. Now let's move on and understand what frag coordinate and frag color really are. So GLSL provides us with a default output, which is GL underscore frag color, and a default input, which is GL underscore frag coordinate. And what the input consists of is the coordinates of the pixel that the thread is working on. So we can know that the location of the pixel which is being worked on, and we can identify that particular pixel from its location. And since this is the only input that a thread gets, which is varying from essentially thread to thread, it is known as a varying. Now, step and smooth step. Step and smooth step are two inbuilt interpolation GLSL, which they are hardware accelerated, so they're very efficient, and they form the basics of uh, writing shaders essentially. So if you're writing any shader, chances are that you'll be using step and smooth step somewhere. Now, to explain to you how these functions work, I'll give you another shader demo. Before that, I'll just to show you how frag coordinates work, I have created another small demo here. And by the way, if you want to test out how your shader looks before you start integrating it into your Flutter application, you can go onto this site, https://editor.thebookofshaders.com. And here you can write your shaders and see them being updated, as I'll show you right now. You can see them being updated in real time and basically test them and experiment with them while you write them before you integrate them into your application. So to show you how frag coordinates work, here we are taking the frag coordinates, we're taking the first two elements of the xy from it, and then we divide it by the resolution to normalize it. We get another vector, we get another vector st and give it this value. Essentially, we initialize a variable called st and give it this value. And then in the output, which is the frag coordinates, we make it so that the position of the pixel and the dot x and the dot y values, that is the position of the pixel, becomes the r and the g value, which gives you a gradient of between red and green, as you can see here on screen. Now, for the step and smooth step, first I'll explain to you the easier one, which is step. Right. Now, as you can see here, we have half of the screen as black and half of the screen as white. So what is happening here? We are first normalizing st as we did in the last shade I showed you. We're taking the frag coordinates and dividing it by the resolution to uh, normalize it. And then what we do is we write float value equals step 0.5 comma st dot x. Now what this does is it will take this st dot x, and for each, as I explained, the coordinate varies for each pixel. For each pixel, it will check the x value. It will see if it's greater than this edge here, which is 0.5, which, since it's normalized, will be every point after the first half of the screen. And for every point after the first half of the screen, it will return 1. And for every point before the first half of the screen, it will return 0. And here, when we do vec3 colors equals vec3 of val, and we have a float here as val, what this really is doing is the same as val, comma, val, comma, val. So it creates a vector which is the same as val, comma, val, comma, val, and puts that here. So for every point before the edge of the screen, it will be giving you 0, comma, 0, comma, 0, comma, 1, which is black. And for every point after that, we'll be getting 1, comma, 1, comma, 1, comma, 1, which is, as you see here, white. So this is what step does. It allows you to change a value from 0 to 1 at a particular edge. Now, what is smooth step? I'll comment this out and bring back the code for smooth step. There we go. Now what smooth step does here is, you can see the explanation here. It is in the for the plot function here. It is something made for smooth transitions. Now what it will do is, this is the syntax for a smooth step. It has an edge 1 and edge 2 and the variable. So if this variable, which here is st.y, and we are getting our st from here because it's a function and takes st as an input, for st.y, it will first check if it is less than, sorry, pct minus 0.02, and if it is, it will return 0. If it is greater than edge 2, it returns 1. And if it lies between these two edges, what it will do is it will return a point between 0 and 1 according to where it lies between these two numbers. So it will give you a smooth transition. And here what we're doing is, in the plot function, what we're doing is, it creates a thin horizontal line and it smoothly transitions from the horizontal line to the background. And how it does that is this first thing here. It it smoothly transitions from 0 to 1 before PCT, and this here smoothly transitions from 1 to 0 after PCT. And when we subtract the first step from the second step, it does is creates a narrow band or a soft line. Now what we need to understand is that it is not that we cannot create a line without smooth step. We can do this with step also, right? So as you can see here is since we modified the plot function here, the color also changed for the band, but I can also vary the thickness. So as you can see, the line itself is not purely due to the smooth step. The step can also be used to create a line here. But as you can see here, it uh, goes from this pink color to the background color directly. There's no transition happening. But in the previous code that we had, there was a smooth transition. It was slowly changing from green over to white. As I'll just show you when we go back to our initial code here. As you can see, it fades into the background with this sort of blurred effect at the edges. That is created by smooth step. So here, what we are really doing in the code, we have our st, as we have previously explained. We have a float y, which is a smooth step from 0.1 to 0.9 through st.x. Now, this y is the reason that from 0.1 to 0.9, we see a transition here happening in the background, while from before 0.1, we have pure black. After 0.9, we have pure white. Because it after 0.9, it is going to return 1, and before 0.1, it is going to return 0. So that is the color variable which is happening here. Here we call the plot function in it, where it goes here, and this smooth step, this st.y, uh, due to utilizing the smooth step function here, is also why you see this line taking this shape here, which is the shape of the smooth step function. Whereas you can see the line uh, is having zero height essentially here till 0.1 or 10% of the width has passed. And at the end, in the last 10% also, uh, it has full height or it has reached the top edge. And in between, it is transitioning according to the graph of the function which is utilized by smooth step to interpolate between the two edges. And here all we are doing is we are removing the portion which is uh, set here by the plot line, and we are giving it the color through the plot function, which is through PCT. So PCT represents the coordinates which are set here through the plot line, and we remove that from the background color that we have, default background gradient that we have here, and we give it the value that is given to it by the PCT or the plot function. And then we provide this color value to our frag color, which allows us to render this shader. And this might seem simple right now. Step and smooth step are do form, however, the very basics of writing shaders. And through what I have taught right now, you can write some beautiful shaders if you really gain command over the maths behind it. So I'll just give you a demo of how you can write a beautiful and amazing looking shader. So just a few lines of code and to the very basics that we have already been introduced with. So this shader here that I am viewing on this great site shadertoy.com, where you can go to take inspiration for shaders. Uh, it utilizes just 20 lines of code, and with a few mathematical functions like sine and mod and length. Uh, Through that, it is able to create this beautiful effect which you see here. So for shaders, what you need to realize is that just the basics are enough to make some beautiful effects. What you really need to do is you need to have a really great command over the very basics of how these functions work. Now moving on to the next slide, colors. Now what are we doing here? For any pixel, we are essentially at the end defining which color it takes. So color forms really the very basic of any fragment shader, and hence so does mixing them. So one of the most basic and most important ways, and also if I might say one of the most easiest to understand ways of manipulating shade colors and shaders is through the mix function. Now let's see how the mix function works here. Here, first before we move on to the mix function, I want to uh, let you know how you can manipulate the vec4s that we have been seeing all over the place. Now, what exactly is vec3 and vec4? It just represents the length of the vectors. So vec2 has two elements. It's a vector with two lengths. A vec3 is a vector with three lengths, and a vec4 is a vector with four lengths. And how do you access the elements? As you might have seen in the previous code samples, we did vector.x or vector.xy. So to access any of the elements that are in these vectors, you can use any of these formats. You can index them through numerical ways, through RGB and alpha, through XYZ and W, as well as STPQ values. Now, what is happening here in this shader? We have two colors, two arbitrarily defined colors here to uh, just show you. I'll set this. This is the color A, and this is the color B. And what we're doing here in the main is we are taking a color variable which is initialized as just 0, 0, 0, and then we are creating this variable float which is PCT. And what this does is it is the absolute of a sine wave of the sine of the uniform time input float that we get. So this is the uniform time input which essentially shows you the time from which the shader has rendered, and then it creates a sine wave, and the absolute makes it so that it is a positive float which varies between 0 to 1 in a sinusoidal way, in a sinusoidal fashion. So what does this mix function do here? It mixes the two colors, color A and color B, and PCT here represents the percentage of the colors. So PCT as we get here is varying according to time, and so the degree of mixing of each of the colors varies over time. And when you provide this to the output or the frag color, what you get is this beautiful fragment, the color of which varies from color 1 to color 2 as the amount of color 2 increases with time. And then it goes back to 0 in a sinusoidal fashion. So that's how mix function works. Again, it looks really simple, and in isolation, it is really simple. But when you mix these functions together, you can create some really beautiful effects. Now, making basic shapes. Now, if you want to create a beautiful shader, I assume you'd also want to create some shapes. You might want a square or an edge like this or a circle in it. Now, how do you create these shapes in your shaders? Let's check it out with this demo here. As you can see, we have the same, in this demo, we have the, I'll just reload this because resizing the screen seems to have caused the shader to go away. But yes, I'll reload this so that it re-renders again. Huh, great. So we have the shader here, and it is the bottom two edges of a square. Now, how are we creating this? For doing this, we'll be again using the step function that we talked about just a few moments ago. So the step function here, what is this doing? It is taking a vector which is 0.1 here, so 0.1 comma 0.1. It is taking st, which is a normalized version of the frag coordinates, and it is applying a step function on it. So for any st having a value greater than 0.1, it will return 1. So what it will do is, if you have 0.1 comma 0.1 and the value of st is say 0.9 comma 0, so it will return to you 1 comma 0 because 0.9 is greater than 0.1, but 0 is not greater than 0.1. So that is how the step function will work here. And then what does this PCT do here? It multiplies the x or the first element of this BL vector with the second element of the BL vector. So what this will do is it works essentially as a logical AND operator. So when you multiply 1 and 0, you get 0. And when you multiply 0 and 1, you get also 0. So this will return 1 only when both the coordinates are above 0.1. So that is this region right here, which is this white region. So for all of this white region, you get 1 comma 1. And for all this black region, which is having at least one of the coordinates below 0.1, you get 0 comma 0. And when you put this in vec3, it will extrapolate that to 1 comma 1 comma 1 and 0 comma 0 comma 0. And when you put it in your frag coordinates, you get white and black, allowing you to give this border. Now, what if I wanted to create a complete square? All I need to do is comment out these two lines. And it applies the same step function here as well. All it does is it reverses the st to 1 minus st. So for all of the values of st which becomes greater than 0.9, this value becomes lower than 0.1. And what that in turn does is makes it go to 0, 0, 0, which is the RGB port 0, 0, 0, 0, which is the RGB code for black. Or in this case, the opacity is 1. So 0, 0, 0, 1, which returns you black. And 1, 1, 1, 1, which, as we all know, is white. Uh, Now that is for the first shape here that we saw, this L shape. Now what if we wanted to make a circle? We have this demo here for that. So another great function that GLSL provides to us is a distance function. And what this distance function allows us to do is it allows us to find the graphical distance between two sets of vectors. So if you have ST and you have the vector 0.5, 0.5, it will return the distance between these 2 points, assuming they were on an x and y coordinate plane. So it will return according to this formula here, which is the square root of the square sum of squares of x1 minus x2 raised to the power 2 plus y1 minus y2. So this is the sum of the squares of the differences between the x and y coordinates of the 2 points that we are talking to here. And we have fixed one of these points here which as the center of the shader, because here we have a normalized version of the frag coordinates. So 0.5 comma 0.5 or vector 0.5 represents the shader of the screen that we center of the screen that we see right here. And what this PCT does is it gives you the distance between ST and this vector 2. So through this, what we do essentially is it will return to us the distance between any point on the to the frag coordinates and the center of the screen. And all we do is we extrapolate that single float value, the single float PCT, to this whole color. So what this is essentially is this is a vector of having length 3, which is PCT, comma PCT, comma PCT, or distance from the center, distance from the center, and distance from the center for each and every coordinate. And according to that, it will render the color here. So what this is again is PCT, comma PCT, comma PCT, comma 1. So this here is how you can render this circle. Because essentially what is a circle? A circle is just a set of points which are equidistant from another point. So when you change the color of a set of pixels according to its distance from another pixel, you get a circle. Now, what if you wanted to make a solid circle and not this varying darker in the center and lighter in the uh, on the edges circle? All you need to do is comment out this part and create a simple step function. And here you go, a solid circle. Want to reverse the white and black? All you need to do is subtract 1 from it. So what this does here is it creates a step over the distance. So if uh, here I have it set as 0.4 instead of 0.5 because the 0.5 would touch the edges of the screen, and I think 0.4 just looks prettier. So it checks the distance that any point has from the center of the screen, and if it is above 0.4, it renders it as black, and if it is not, it renders it as white. So because the step function, if it is if 0.4 is greater than this portion right here, it will give 1, and if it's 0.4 is less than this portion, it will return 0. So it will return 0 comma 0 comma 0 comma 0 for all of all of these points which are farther than a distance of 0.4 from the center of the screen, and that will cause it to become black. And the center of the screen, or this circular piece of area around the center of the screen, becomes white. So this is how you render basic shapes of a shader. And these functions are the building blocks of writing a shader. And when you integrate these into one another, you create a shape, you add colors to it, and you make them vary with time. You get some really beautiful effects as you saw here. And I'll show you some more advanced shaders at the end of this video, which will help you appreciate really how beautiful shaders can be. Now moving on to the next slide. Translation and rotation. Now again, one of the more important things that you want in a shader is you want to make things move. And how can you make them move? You can make them go from X to Y, or you can make them rotate around an axis. So how do you do that? For that, you have to manipulate the coordinate system itself, and that is done through transformations to 2D matrices. Now, for this, you need to really visualize the screen as a set of coordinates which vary from 0 to 1 and 0 to 1 on the x and y axis. And when you have that graph in mind, it really becomes a lot easier to imagine how you are manipulating this graph to make objects move from, or elements in shaders move from one place to another or rotate. And again, I'll demonstrate this through a demo so that I can better explain to you how this really works. And here we have a box which is moving around the screen. For the box, I am calculating essentially through this where I'm just calculating the bounds for centering it, and then I'm using a step function to create a square, and I'm multiplying the two steps with each other so that I can create both edges and essentially create a white square here. So this box part is not so important in explaining rotating and translation because it is more relevant to the last slide and how you create shapes in a shader, and it is essentially just a reversal of the first shader that I showed to you in the making shapes thing, where it was essentially a white box with a black border. That it is really the same thing here. Now, in the main function, first we'll talk about the translation thing. This subtraction of 0.5 and addition of 0.5 becomes more relevant when we talk to the rotation part. So I'll not talk about this here because right now with all of the rest of the code commented, uh, it really is just being cancelled out. But to translate, what we are doing here is we are adding this vector to the coordinate system, to the normalized coordinate system that we have here. We're adding this vector called translate. And what does this vector translate? It is a vector of length 2, with the first one being a cos of time and the second one being a sine of time. And we multiply it by 0.35. Now, what is the 0.35? It is nothing but it defines the radius of translation or how far you go from the center. Uh, so what we are really doing when we add something, when we add this varying with time constant, uh, not exactly constant. Well, when we add this variable which varies with time to the st variable, what it is doing is it is taking our coordinate system and shifting it with an amount which is provided by the translate vector. And this translate vector, since it varies with time in a uh, the x-axis is varying cosine in a cosine manner, and this y-axis is varying with sine. The it translate in a circular manner. Now, if you wanted it to translate in, say, an oval, all you needed to do is manipulate this here, and as you can see, the shape turned into a more oval-like shape. So this thing, which varies with time, allows us to sort of make shift the coordinate system with time, and that creates the effect of translation. And if you wanted to say play around it with it more, all you need to do is do the square of this. And it will change uh, the cosine values to move in this C fashion. Now, why am I extensively using sine and cosine? So the reason that you usually extensively use, say, sine and cosine in shaders is sine and cosine are limited to always return values between -1 to 1. So when you take the absolute value of them or you use the square of them, you get a float which comes between 0 to 1. And that is really very versatile in shaders because we are really just dealing with floats in shaders. So I'll reverse this part here before I move on to explaining to you how rotation works. And before I do that, I'll just show you this, make it rotate and show you how cool it looks. So as you can see now, the square instead of just translating, is also rotating around its own uh, around the shader center. And how does it do that here? For that, we need to go to this function, which is uh, returns a matrix and uh, a rotate 2D function. So what does this do is it returns a matrix which you give it an angle and it will return a matrix, a 2D matrix, having the elements cos of that angle, the negative of sine of that angle, the sine of that angle, and the cos of that angle. So what this is just a function which is mathematically created a function uh, which is the formula for the rotation transformation by an angle theta. So this is a formula essentially that you can remember, which is the formula for translation by an angle of theta. And we use this formula here, and we multiply it by the coordinate system that we created here. And before we multiply, we just subtract it by 0.5. Now what happens when you subtract a coordinate by 0.5? When you're adding or subtracting to a coordinate system, you're shifting the center and shifting the entire coordinate system. So that was what was happening in the translate version here. When we were adding it to the coordinate system, we were shifting the entire coordinate system. And again, when we subtract it by 0.5, we shift the entire coordinate system to have the center of the screen as the origin, because it is again a normalized coordinate system, right? So we are shifting it, the origin, to the center of the screen. And when we multiply it with this rotate 2D function, which is rotating with the function with an angle which is varying with time, according to time, you're essentially uh, transforming the entire coordinate system. And how are you transforming the entire coordinate system? Since you're using the it with time, and you're using the formula for rotation by an angle theta, and again you have shifted the coordinate system to center, it makes it rotate around the origin uh, of the uh, of the shader or the coordinate system that you're using here, and the origin of the coordinate system that you're using has already been shifted to the center. And now after we define our translate here and add the translation motion also, before we give it this coordinate system to our frag color to make it render it, we need to shift the coordinate space back so it can correctly render. So for that, we add the 0.5 that we had initially subtracted here, and we add it to the color, and voila, we have this beautiful shader which spins around the center and also rotates. And yes, so before we move on to the next slide, which is how you integrate the shaders in Flutter, I want to help you understand how why this I created this presentation and why why shaders are so great. Shaders can really be very beautiful. What we have discussed here is just we scratched the surface, or what is the very uh, basics of shaders and how you can really get into writing shaders. But when you master the basics and you start getting a little creative with it, you can make these beautiful fragment shaders. For example, this seascape that you see here, this is not a video, but a shader. In all of 200 lines of code, this was created by a person by who identifies as TDM in Shader Toy, and he was able to create this completely model. As you can see, you can adjust the speed, the frequency, the color, everything of the sea, and with just a little bit of maths and with no textures, also he was able to create this beautiful, uh, realistic ocean shader. And the website that I'm using for to help you see this shader is the Shader Toy website, which you can go ahead and explore. And it has a lot of uh, shaders that you can take inspiration from. Another shader that I'll show you to just really help you appreciate the beauty of shaders is this beautiful uh, solar system shader. This again, really not a lot of lines of code, just with 175 of lines of code. And while I know that lines of code is not usually a metric to measure the greatness of the code, but I really want to help you appreciate with how little code and how with just understanding of maths and understanding of how shaders work, we can create these beautiful effects. And they're really efficient too because they utilize the GPU instead of the CPU. And now moving on to why we're here, utilizing shaders in Flutter. I have in this counter app integrated the shaders because I wanted to show you how you can have a normal any app essentially and make a screen of it part shader. And as you can see, we have a beautiful shader being rendered here. Uh, it is rendering slightly slowly, but that's more because my laptop is running OBS Studio as well as Android Studio and a lot of other applications at the same time. But yes, a beautiful shader is being rendered here, and I'll show you the code of how you can create and render such a shader yourself. For that, all you need to do is first you need to go to your pubspec.yaml, and you need to in the assets and under the assets really, you need to create another one which is with another key with the name shaders, and in that you need to add a shaders folder which you create in the root directory, as you can see here, and in that you put in a shader and you define that shader here in your pubspec.yaml so that your entire application has access to it. And you also install a package known as flutter underscore shaders through flutter underscore shaders. and then you get this package, you add a shader to your assets. And I'll just show you the shader here. It is a box sandwich. Well, of course, it's slightly complicated and really beautiful, and credits to the person who created this shader here. But right, it is a shader written the same way that I just demonstrated to you now. It's uses the same uh, uniform variables. It specifies your precision here, and it uses a few function, and it returns your frac color. And we define this in the pubsec.yaml so that the entire application has access to it. And you create another screen, a stateful screen, in the same way as you usually do. And you go over here, and when you are extending the screen state, you extend the state and you provide a ticker along with it. Now, what does a ticker do? A ticker is something which calls its callback every time a frame is animated. So when you need to create a sort of timeline, you need to essentially, when you have an uniform input, right? You have the u underscore time uniform input. You need to provide that to a shader through Flutter, right? So that input of time, or that uh, essentially illusion of time passing, is created when every frame of your application is animated through this ticker here. So you create a variable time, and you initialize a ticker in there in its state, and every time this ticker or a frame is created, this ticker, what it does is it does this callback, which adds 0.1 in the time, and the set state calls a re-render, right? And this starts the ticker here. And the dispose function, you want to dispose of the ticker so that you don't create any leaks. And again, you have the standard some standard Flutter code here. And what you really need to look at is this portion here, a shader builder. You, from the package that we installed, you utilize a child called shader builder, and you give the asset key that we defined in the pubspec.yaml to tell it which shader to use. So you give it shader slash shad1.jsl, which is the shader that we were using here. And in the child, we are here using a size box, right? And for a shader builder, it requires a child, it requires an asset key, and it requires a builder function. So for the builder function, it takes the parameters of the context of the shader and of the child, and you need to return an animated sampler because you're providing an animation. So for that animated sampler, you again need to create a builder for which you need an image, the UI image, the size, and the canvas. And in that canvas, you're rendering in the shader here, and this shader is taken from this asset key. And for the shader requires some uniform inputs from the CPU, right? That I told you about your u underscore time, your u underscore resolution, your u underscore mouse. So all of these are set using this set float, and zero is the index. So when you go into your shader, when you use set float zero comma time, it will take up your first uniform variable that you defined here and set its value to time. So here you are setting u underscore time to time. And now you might see that we have only one more uniform variable left in the shader here, but we have two set floats. Now, since we are providing a vec2 as an input, which is a vector of length 2, you need to utilize these set floats individually to provide it with the value of the width and the height so that it gets the resolution of the vec2. And then you just draw the shader onto the canvas using this draw paint uh, function. And there you go. You have a beautiful shader showing up on your Flutter screen. And that was my presentation on how you can utilize the basics of shaders to create some beautiful effects in Flutter. Thank you. If you want to explore more about shaders, you can look up the book of shaders online.